Today we're going to look at the interesting relationship between the derivative of a function and the derivative of the inverse of that function. It's interesting, especially if you're trying to find the derivative of an inverse of a function, but finding that inverse is difficult. So let's first do a little review from pre-calculus about inverse functions. There's probably a lot that you remember. I know there's a lot that you remember about a function and its inverse. You'll probably remember that a function and its inverse, when graphed, are mirror images over the line y equals x. You probably know that the domain of a function is the range of the inverse and vice versa. You probably know too, if you compose one function, the inverse into the original function. So in other words, plug the inverse into the original function, x is going to be the output. And same with the other way around. If you plug the function into its inverse, the output would be x. So we're going to use a few of those ideas. And we're going to look at finding derivatives of a function or of the inverse based off of information we know. So first things first, let's look at a function like f of x equals 1/2 x cubed. I think you'll probably remember, and if you don't, this will be a good reminder, how to find that inverse. So if we rewrite this as y equals 1/2 x cubed, that's easier to see. And then to find the inverse, we're going to switch the x and the y. So if we switch the x with the y, they're now in new places. And then we solve that new equation to isolate y again. So I'm going to multiply by 2 on both sides, so that'll make this 2x equals y cubed. And then I'm going to take the cube root of both sides. I probably should have written that a little bit further over, so now it's the cube root of 2x. The way we write this then, that the function is 1/2 x cubed and the inverse is the cube root of 2x. Okay? That -1 power does not mean 1 over the function, that means the inverse of the function. A little confusing, but that -1 means the inverse of the function. So let's look at the other relationships that you guys know. You know that the domain and the range are switched. So let's look at what that might mean. For example, if I let x equals 8 in the original function. So if I plug 8 into the function, not 8, that's way too big. I don't want to do that in my head. Let's put 2 in for x. So 2 cubed is 8. Maybe that's what I was thinking. And then 1/2 of 8 is 4. Okay, let's try it on the other side now. If I put 4 in, so remember the domain and the range are switched. The 4 was the y value here. That means 4 is going to be the x value in the inverse. So if I plug 4 into the inverse in place of x, 2 times 4 is 8. The cube root of 8 is 2. So we can see that the x and the y value for a function and its inverse are flip-flopped, are switched. The domain becomes the range and the range becomes the domain. Now let's look at the derivative of each of these, because that part gets interesting. Let's look at the derivative of f of x. I'm going to draw it's okay. I'm going to find the derivative of f of x. So I'm going to multiply by, I'm going to use power rule. So that's 3/2 x squared. I'm going to plug 2 in, and I'm going to see what that derivative looks like. So I have 3/2 times 2 squared, which is 4. 4 times 3/2 is 6. Okay, keep that in mind. Now let's find the derivative of the inverse function. I'm going to get to use the chain rule. So I'm going to rewrite this first before I start to differentiate. 2x to the 1/3. Now, to find the derivative, the notation is really interesting. It's the inverse and then the derivative of that inverse. Okay, I'm going to use the chain rule, so I'll bring the 1/3 out in front without changing what's inside, subtract 1 from the exponent, and then multiply by 2. Let's simplify that a little bit. Now I want you to listen carefully to this part because you will be doing all of this without a calculator, and that 2/3 power can be done in several different ways. So I'm going to rewrite this just a little bit larger. I can multiply this 1/3 times that 2. They're both to the first power, so I'm going to make this 2/3. And then for that exponent, I'm going to make that a positive exponent by writing it as 1 over 2x to the 2/3. Now that 2/3 power can be written a couple of different ways. You can write this as you can write this as 2x squared and then the cube root of all of that. That's one way to write it, and sometimes that's more difficult because you have to square what's under the radical, which makes the number really, really big, and then try to take the cube root of that number all without a calculator. Another way you can write it though, because this is all multiplication, the exponents are all multiplied, so it doesn't really matter what order we do it. I can rewrite this as the cube root of 2x and then square that result. And that'll make the numbers a lot smaller, so a little bit easier to work with. Okay, so all of that, that's the derivative. Now I'm going to use the x value for this inverse function. Remember the x value was 4, and I'm going to plug 4 into this. And I'm going to see what my result is. So I've got 2/3. And this is where it's going to be nice, because if I would have plugged 4 into this original, 4 times 2 is 8, 8 squared is 64. And if you know the cube root of 64, great. But if that number would have been even larger, so if I was really mean and used something even bigger, that would have made the math a little more difficult. So instead, I'm going to keep it like this. I'm plugging 4 in for x. I'm going to say the cube root of 2 times 4. So the cube root of 8 is 2. 2 squared is 4. If I rewrite this, I've got 2/3 times 1/4. And if I simplify that, I get 1/6. So let's take a look for a moment how these two things might be related. So we had the derivative of the original function with its input of 2, and that derivative was 6. Then I found the derivative of the inverse with its input of 4, and that derivative was 1/6. Keep that relationship in mind. Let's try another function. Let's look at, how about logarithms and exponentials, since that was something new in this unit. Okay, I'm going to use a different color now because I want this to stand out. Blue. So let's look at the function, the natural log of x. And let's find its inverse. To find its inverse, we're going to switch the x and the y. So x equals the natural log of y, and then we need to isolate the y. So I'll rewrite this logarithm again as log base e of y. That's easier to see that we need to rewrite this as an exponential in order to get y isolated. So in this case, y is going to equal e to the x. And you might have already known that those two functions were inverses of each other, but if you didn't, now we know. So we've got the function, the natural log of x, and we've got the inverse, which is e to the x. All right, let's choose a point. Oh, let's see. If I use e as the input for the original function, you can use any value. I'm using e because it's good. And then I take the natural log of e. This is why I chose e, because I want you to think about what is the natural log of e. In other words, log base e of e. What is that equal to? That's equal to 1 because that logarithm is an exponent. E to the first is still e. Okay, so that means on this inverse, if I plug 1 in for x, if I switch the domain and range, if I plug 1 in for x, e to the power of 1 will give me an output of e. Those two things are, the x's and the y's were switched, the domain and the range were switched. Okay, let's find the derivative of each. The derivative of the natural log of x is 1 over x. If I replace x with the input, so if I replace x with e, I get 1 over e. Okay, now let's look at the derivative of the inverse. The derivative of e to the x is itself, like we saw, that was that special case. The derivative of e to the x is e to the x, or e to the x times the natural log of e times the derivative of the exponent, but all of those are 1. Okay, now if I replace x with the input, so in our case, in this inverse, the input is 1, I have e to the first power, which is e. Okay, let's look at this. The derivative of the function with its input is 1 over e. The derivative of the inverse with its input, its relative input, those two, the inputs and outputs are related here, was e to the first, or e over 1. I think you're probably starting to see a relationship here. Let's do one more. What do you say? Green, I think, this time. Okay, let's do another one of these. Let's say the function is tangent x. The inverse, I'm not going to spend the time to find it this time. The inverse is arctangent x. Barely fit that on there. I'm going to choose a point. That's interesting. Let's choose, let's say pi over 4, because I know that the tangent of pi over 4 is something pretty easy. Tangent of pi over 4 is 1. And the arctangent of 1 is pi over 4. All right, let's do the math. If we find the derivative of tangent x, that's secant squared x. So I'm going to show you why this is going to come in handy, because finding the derivative of tangent x is not hard, but then trying to figure out what the secant squared of pi over 4 is can trip people up. So I'm going to show you that, the relationship is going to come in handy. I'll show you why. So let's find the derivative at pi over 4. This tends to trip people up. We have secant squared of pi over 4. Not something that we're all familiar with, but we do know that secant squared is equivalent to 1 over cosine squared. So what we're trying to say here then is it's 1 over the cosine of pi over 4 squared. Now the algebra gets fun. Let's see, cosine of pi over 4, that's root 2 over 2. And if we square root 2 over 2, the square root of 2 squared is 2, and the denominator, 2 squared, is 4. 2/4 is the same thing as 1/2, and 1 divided by 1/2 is 2. Yikes. A lot of places where mistakes can happen. The nice part, though, is the derivative of arctangent is actually not so bad. We know that it's u prime over 1 plus u squared. That was what we found the other day. So if we find the derivative of arctangent, we know that derivative of arctangent is u prime over 1 plus u squared. And in our case, u is just x. So the derivative of arctangent, something you should just know from now on, is 1 over 1 plus x squared. U was x, the derivative of x is 1, so it's 1 over 1 plus x squared. And we know the input is 1 on this case. The input was 1, so if I replaced x with 1, I get 1 over 1 plus 1 squared, or 1/2. So we're noticing, I hope you're noticing, that the derivative of a function and its inverse at that correlated point, so this point that they share is really important. As long as we're looking at this correlated point, that point that they have in common, if you will, the derivatives are inverses of reciprocals of each other. The derivatives are reciprocals of each other. So in this case, it actually would have been easier to find the derivative of the inverse and then find the reciprocal of that if I was looking for the derivative of tangent at pi over 4. Because you can see that all of the math that it took to find the derivative of tangent at pi over 4, there was some algebra there where some mistakes could have been made. However, finding the derivative of arctangent, when you know it, that was a really simple problem, turns out. So the derivative was 1/2, so we knew that the derivative of the function would have been 2 over 1, or the reciprocal. Okay, I'm going to stop here, and in the next video I'm going to look at how this might be useful. Because so far, we've been looking at functions where we can find the inverse, or finding the inverse is something that's easy, but it's not going to always be that way. We'll look